So when I got asked to come, I said I would answer questions, and they said I should give a talk. So I'll give a little talk about one of the most exciting developments in physics recently. But my goal will be to just get you, maybe confuse you, so that you can ask questions. And then, and so we can spend as long as you want asking questions. And if you don't have any questions, I'll just go for a coffee. Okay? Good. What I want to talk about is the universe, and we'll see if the universe will cooperate. There we go. This is the universe. This is a Hubble Space Telescope picture of galaxies. And for the young people, I was just talking this morning, but it may be hard for you to appreciate how much our picture of the universe has changed in the last 100 years. But I said it this morning, I'll say it again because I'm very happy. My mother is 97 years old, and she just told me before I left, I arrived yesterday, that her mother, who I thought was born in Poland, was actually born in the Ukraine. So I feel like I'm coming home, which is very nice. But she was born in 1921. But in 1925, the whole universe consisted of our galaxy, one galaxy, the Milky Way. That was it for science. And now, we now know when we look out that in the universe that we see, there are more than 100 billion galaxies, each containing 100 billion stars. And here's just a small slice of the sky. And you can see, if you look at the blue galaxies, and the very faint blue galaxies are maybe 10 billion light years away. That means the light from these galaxies took 10 billion years to get here, so we could take the picture. But our sun is only 4.5 billion years old. So that means the light left from these galaxies before our sun and Earth even existed. And if you think about it, there may be civilizations that existed on those galaxies 10 billion years ago that are now long gone. Because in 5 billion years, our sun will burn out, and we'll be long gone and forgotten. And if someone in a galaxy here 5 billion years from now, 10 billion years from now, some civilization takes a picture of our galaxy as it looks now, by the time the picture's taken, we'll be long forgotten, and everything that we've done is long forgotten. So enjoy it while you can, okay? But I just wanted to point this out because every picture of the universe, if you look at it long enough and deeply enough, should inspire you to think and wonder and awe. The real world is amazing. And since I've been a scientist, when I was your age, we never had pictures like this. We only imagined what the universe would look like. And it's been amazing to me in my career to see things that we only dreamed of when I was a student be realized now. And you're lucky and living at an interesting time that I hope for many of you that the changes that take place in the next 40 years will be as dramatic as have taken place in the 40 years that I've been doing science. And one of the things that has been imagined, and was first imagined by Albert Einstein in 1916, was the possibility of gravitational waves. Albert Einstein showed that gravity is a property of space and time. That what we experience as gravitational force is really the curvature of space. And every mass, like me, curves space around it. But that means when I do this, I'm producing a disturbance in space. I'm moving my arms, and I'm producing a disturbance in space. And just like dropping a pebble on a pond produces a wave on the surface of the water, when I do this, I produce a disturbance in space that propagates outwards. And Einstein first realized that in 1916 or so. In fact, 20 years later, he actually thought he made a mistake and that gravitational waves didn't exist. Einstein made mistakes. You should feel good. We all make mistakes. Hopefully we learn from them. But it was long realized that gravitational waves are so weak that we would never thought we'd be able to detect them, because gravity is the weakest force in nature. So even though I make a ripple in space that moves out when I do this, it's so small that you'd never be able to measure the gravitational waves that are produced by my arms. To produce very strong gravitational waves, you need big masses, bigger than me, bigger than the Earth. You need cataclysmic events. But what happens, but at the same time there are gravitational waves going right through this room all the time as we sit here. And what happens when a gravitational wave comes by this room? Well, let's imagine a gravitational wave is coming out of the board. What happens is space gets smaller in that direction and bigger in that direction, then smaller in that direction and bigger in that direction. Space itself changes. So in this room, right now, the distance between those walls is getting smaller and bigger and smaller and bigger and smaller and bigger because of the gravitational waves that are going through this room. But the effect is so small that most of you don't detect it, unless you were drinking too much last night, and maybe then you do. But maybe you're all too young to drink, I don't know. But in any case, it's happening. But the effect is so small that certainly when I was a student, we thought it would never be detectable. This is the wave going in and out. If you want to see the whole wave, it looks like that. But it's pretty to look at, but there's not much information there. So the question is, can we detect gravitational waves? And I'm a theoretical physicist. So that means I just write on pieces of paper and I talk and I think, but I don't do anything. But experimental physicists do things. And I'm in awe of my experimental colleagues because they take the ideas that we have and try and test them. If gravitational waves exist, this is science, not religion. You have to be able to measure them. If you can't measure something, from the point of view of science, it doesn't matter. Only if you can measure it is it science. Only if you can measure it in principle. So, some brave colleagues 50 years ago thought maybe we could measure gravitational waves not from my arms moving around, but from the most violent events that happen in our galaxy and other galaxies. What would that be? Well, maybe there are 100 billion stars in our galaxy. Maybe two stars collide, and that's a dramatic event. Well, two stars colliding is pretty dramatic, but first of all, most stars don't collide very often. But stars even two stars like our sun colliding probably would not produce gravitational waves which are strong enough to detect. But maybe there are huge black holes, stars that have collapsed and are so dense that a mass the size of our sun would collapse down to the size of Kyiv, be so dense that one teaspoonful of material would weigh billions of tons. If those objects exist in our galaxy or other galaxies and they collided, maybe we could detect gravitational waves. So over a period of 25 or 30 years, people built detectors. And this is the first large gravitational wave detector. It's in the United States, in Hanford, Washington. There's an identical one in Louisiana. One is in the north and one is in the south of the United States. There are two of them for reasons I'll describe. They're identical. And what they are two tunnels at right angles, each 3 kilometers long. And in principle, if a gravitational wave came down from above, what would happen? This tunnel would get a little bit smaller, and that tunnel would get a little bit bigger. And then this tunnel would get a bit longer, and that one would get a little bit shorter. So in principle, it's really simple. All you have to do is measure the length of this tunnel and measure the length of that tunnel and watch it change. Easy. Not so easy. Because you can calculate the effect of a gravitational wave from two black holes colliding in our galaxy or a nearby galaxy. How big would the effect be? And this is why I'm a theorist and not an experimentalist. Because it turns out you'd have to measure the length of this tunnel, which is 3 kilometers long. You'd have to measure a change in the length as a gravitational wave came by. The length would change by an amount equal to 1/1000th the size of a proton. 1/1000th the size of a proton. Who can do that? We can. Not me. But amazingly, this detector was built to be able to do that. First, it only got to 1/100th the size of a proton. And it was turned on for 10 years and no one saw anything. But then it was improved. And in 2015, I think, it was turned on. And it had the necessary resolution. If these black holes were colliding, this should detect it. Now, there's an important lesson here, because a man named Ray Weiss, who I used to know when I did my PhD at MIT, it's a university in the United States, and Ray was a professor there, and he designed this detector, the first detector. And when you turn on a very complicated machine, you want to tune it up, make sure it's working. So he told his students, okay, we'll turn it on and we'll see if it's working. Don't take data. Just want to get it working. And the students did something very important, which all students should do. Don't listen to your professors. Yeah, that's probably okay. They took the data, and 1 hour after it turned on, they saw the signal of gravitational wave signal from two black holes colliding in a galaxy 1.3 billion light years away. Now think of that. The signal turned out to last 0.2 of a second, which is the amount of time it took for these black holes to collide. I'll show it to you in a moment. So 0.2 of a second, that signal had been traveling for 1.3 billion years. If they turned on the detector 2 hours later, they wouldn't have seen it. It's amazingly lucky. And as I said this morning to a different group, accidents are incredibly important in science. And the fact that it was there and it just happened to turn on at the right time was amazingly fortunate. Now, how can you measure a difference in length that's small? Well, you use physics, of course. And here is what you use. Use lasers. And you measure basically a distance by measuring the time it takes a light beam to go from one end of the tunnel and bounce off a mirror at the other end of the tunnel. And what we take is a laser beam and split it, and then have it come back. And as the two ends of the tunnel change, you eventually, as you'll see on here, you'll see a wave. But if one of these waves travels a little bit farther than the other, waves will interfere with each other. And if you design it exactly right, so these two waves will negatively interfere, you'll have nothing. You'll have a dark spot on the screen because the peak of one wave will interfere with the trough of another. But if the length changes a little bit, then the interference pattern will change. And you'll see here in a second, you'll see what was a dark spot turn into a light spot. And using this technique of interferometry, you can measure very small time differences and very small length differences. Now, it's much more complicated than that. You actually have to run it back many times. You have to use an incredibly powerful laser. And you have to get rid of lots of backgrounds, because we're measuring time distances that are very small. So if a truck hits a pothole 20 miles away from that machine, it will produce a bigger effect than this. That's why there are two of them, because there's lots of noise in each of these detectors, but we have one detector in Washington and one detector in Louisiana. And gravitational waves travel at the speed of light, so you can calculate that it would take about 8 milliseconds, 8/1000th of a second, for a gravitational wave to get from one detector to the other if it's traveling in the right way. So all you have to do is look at those two detectors, and there's lots of noise, but you look for a signal that's identical in the two detectors, separated by 8/1000ths of a second. And that gets rid of a lot of the noise. That's the first thing. So only in 2015 did we have the technology, and by the way, mirrors are vibrating due to quantum mechanical effects by a much bigger effect than we're looking for. So you have to use very complicated new kinds of atomic physics called quantum optics to play with the laws of quantum mechanics, so the motion of the mirror in this direction is reduced, and it uses the highest level technology we now have. 10 years ago, it would have been impossible. That's for the experiment. But for the theory, we have to calculate what we think a gravitational wave, what effect a gravitational wave would do. That's also very complicated, because two colliding black holes, the mathematics of calculating the gravitational waves is very complicated. Only when we had large supercomputers could we predict a signal. So only in 2015 did we have the theoretical machinery and the experimental machinery. They all came together, and an hour after the detector turned on, here was a signal. This is, you see, half a second. This is a signal in Washington. This was a signal in Louisiana, separated by 8/1000th of a second. When you put the two on top of one another, they're identical. And the noisy curve is the data. The other curve is what you'd predict for two black holes colliding. And you see the prediction and the observation agree almost exactly. This is a gold-plated event. You could never ask for an event this beautiful. And it happened right away. It's amazing. Gravitational waves exist. We see them. And you may say, big deal. But the fact that we see them tells us something amazing about the universe. Let me show you a movie. This is just an artist rendering of what it would look like, of the two black holes, if we could see it. Here are two black holes. We can, comparing the signal to the prediction, it turns out we know that one black hole had a mass of 36 times the mass of the sun, and another black hole had a mass of 29 times the mass of the sun. And the amazing thing is, so we've got two objects that are almost 30 times the mass of the sun, and just before they collide, they're orbiting around each other 200 times per second. It takes us a year to go around the sun. These two objects are moving around each other almost at the speed of light. 200 times a second they're going around, and they produce a signal that has a frequency of 200, and then 300, and then 400 in the audio range. You'd actually hear the signal. And if I had a microphone there, this this will actually also play the signal. You can actually hear it. It's in the audio region. But what you see here is space looks a little weird. That's because the black holes are so massive that if we looked at them, if we could actually see them, which we can't, the space would bend around them. And when I make the movie go, you'll see that the stars move. That's because the light is bending around the black holes as it moves. So watch this. It's slowed down. The whole process takes 0.2 of a second. But you'll see what happens. And at the very end, you'll see space jiggle. And that's the gravitational waves. So let's watch it. So this is just the image of gravitational lensing as space is bending around the black holes, if we could see it. And this is very slowed down. These are actually moving around each other 200 times a second or so. But in the last moment, watch space. It's beginning to jiggle at a frequency. There it was. That was the signal, and it lasted 0.2 of a second, and it caused space on Earth to jiggle a very little bit, but we could measure it. This is a triumph of the human intellect, that we could first know that Einstein could predict that gravitational waves exist, that we could build a detector that could do this, that people would have the courage, the intellectual courage, to spend 30 years of their life building a detector that may see a signal that doesn't exist. Because we didn't know if there were black holes like this we thought there might be, but we didn't know. It's one of the greatest triumphs, in my mind, of the human imagination. And we should celebrate that we're alive during this time. Now, maybe the fact that we can detect this doesn't impress you. I hope it does. But if it doesn't, this should impress you. Nature is stranger than we can imagine, in a sense. And I told you that there was one black hole of mass 36 times the mass of the sun and one black hole of mass 29 times the mass of the sun. They combined together to form a black hole, 36, 29. How massive is the black hole that they form? Your students. 36, 29. 36 and 29 come together to form a black hole. What's the mass of the black hole? Who said 65? Who said 65? No one said 65? Wrong! They form a black hole of mass 62 times the mass of the sun. Where did the other three solar masses go? Into gravitational waves. Mass got turned into energy. Now that might not impress you. But our sun will last 10 billion years burning hydrogen fuel with maybe 1 billion hydrogen bombs going off every second, turning mass into energy. Over the lifetime of our sun, less than about 1/1000th of the mass of the sun, over 10 billion years, will turn from mass to energy. So for 10 billion years, our sun will burn, powering our civilization and everything on Earth for 10 billion years, and 1/1000th the mass of the sun will be turned into energy. When these two black holes collided, in 0.2 of a second, 3 times the mass of our sun got turned from matter to energy, meaning that more energy was released in that collision, in that 0.2 of a second, than is released in all the rest of the stars in the visible universe. And we would never have known about it if we didn't have that gravitational wave detector. Now that is amazing. Okay, you don't look enough amazed, so I'm going to show you something else. Since then, we've detected more gravitational waves, not just from colliding black holes, but there are other objects that are very dense. When stars collapse, if they're very massive, after their nuclear fuel burns, they collapse. And if they're very massive, they collapse into a black hole. But if they're not that massive, what happens? In a period of about 1 second, the nuclear fuel finishes burning, the core of the star, which starts out to be about the size of the Earth, collapses to the size of Kyiv in 1 second, and then it becomes so dense that it basically becomes one giant atomic nucleus of mass number 10 to the 56. At that point, nuclear forces take over, and it can't collapse anymore. So the star collapses, the inside, suddenly it can't collapse. There's a shock wave that goes out and blows out the outer part of the star into what we call a supernova. All the elements that make up your body were produced in stars, because the only elements that were produced in the Big Bang were hydrogen, helium, and a little bit of lithium. But carbon, nitrogen, oxygen, iron, all of that is produced in the core of stars, and the only way it could get into your bodies was if the stars were kind enough to explode, which they did over the last 13 billion years. So that material, you are stardust. You are made of stars. But there was a problem. Everything up to iron is produced in stars. What about the elements heavier than iron? Gold, platinum, all the way up, lead. What about that? Well, they're not produced in the cores of stars. Where were they produced? Well, that was an open question when I was your age. Lots of debate. Well, there was an idea, and it was a really exotic idea. Maybe if you have a star collapse and a supernova, what's left over after the outer part blows out? You have an incredibly dense, giant atomic nucleus. It's so dense that it turns out the protons turn into neutrons, and you have what's called a neutron star. The density of a neutron star is about 100 billion tons in a little teaspoonful of material. And we know there are neutron stars in our galaxy. We can measure them. One could calculate that every now and then, two stars, many stars are in binary pairs. And it is still amazing to me that when one star explodes, it doesn't blow the other star away sometimes, and you could have two neutron stars orbiting each other. When those two neutron stars collide, they're very dense, you produce gravitational waves. But unlike black holes, which are just holes in space, there's nothing that comes out. If two neutron stars collide, gravitational waves come out, but so does a lot of other stuff. Gamma rays and X-rays, ultraviolet radiation, visible light, radio waves, all of that comes out from that incredibly dense collision. So what's amazing is, last year, the gravitational wave detector LIGO and another Virgo detected a gravitational wave event that had the signature of two neutron stars colliding. And they sent out an alert to the whole astronomical community, and all the telescopes on Earth, gamma ray telescopes, X-ray telescopes, ultraviolet telescopes, visible light telescopes, radio wave detectors, all looked in that direction to see if they could see the event, to see if our predictions of what would happen when a gravitational wave, when two neutron stars collided, if those predictions were correct. And here's what we saw. This, by the way, is a neutron star. So this is not a real one, but this is New York City here. And you can imagine this is what a neutron star would look like. It'd be the mass of a sun about the size of New York. And this is a simulation of the event that was detected about a year ago, of two neutron stars colliding. Now, stuff is coming out because these aren't black holes. There's material here. And as they collide, and if I had the sound, you'd hear a little twerp. Now, gamma rays and relativistic jets are emitted. X-rays as radioactive materials come out and decay. Then they turn into ultraviolet radiation. Then the material hits the interstellar medium and produces excitations as visible light. All of those things were predicted. They were all seen. And this solved a problem that had been around since I was a student. How many of you have something gold right now? Maybe a gold ring or a gold necklace? Anyone? Some people. Good. Okay. You're hesitant to put up your hand. It's okay. So our civilization has been profoundly affected by the desire for gold. It's changed lives. People get killed. People try and win it. People destroyed civilizations in their desire to get gold. So human culture has been dramatically changed by the presence of gold since antiquity. And I find it incredibly interesting because where does the gold come from? It turns out the ideas we thought we had 30 years ago was that the place that gold is formed is when two neutron stars collide. Because the heavy elements have many more neutrons than they have protons. And where can you get all those neutrons? When two neutron stars collide, there's all this energy, and maybe you can build up the elements after iron. And the idea was a process called the R process and other processes that might produce gold. Well, we were able to observe with the telescopes that we pointed towards the objects that produce these gravitational waves, the X-rays that came from radioactive materials that would be produced in the collision of those neutron stars that would produce gold. And we saw that in the course of a few days, more than 1 Earth mass of gold was created. So when you now look down at your gold ring, that's where it had to come from. One of the most exotic things in the world. When you're holding gold, you're holding the results of the collision of two neutron stars, the densest objects in the universe other than black holes. And we now know that's the case because we could measure gravitational waves from two colliding neutron stars. So maybe gold is valuable, at least from a cosmic sense. We are not just star children, but we are the children of the most exotic, wild events in the universe. Because neutron stars don't collide very often, very rarely, but the universe is big and old. And that means rare events are happening all the time. Stars explode once every 100 years per galaxy. But there's so many galaxies out there that every second a star is exploding somewhere in the universe. So we can use that if we look out at the universe and try and detect strange things. Now that's where gravitational waves are now, but I want to spend the next few minutes talking about where gravitational waves will be, because I want to talk about something that's of interest to me, which is another source of gravitational waves. By the way, this is the Milky Way seen at night in a beautiful spot, and somewhere out there were neutron stars that collided and produced material that ended up being in our region of the solar system when our sun began to collapse and the solar system began to collapse around it. It's remarkable that that happens. Still amazes me. Okay, there's another way to look for gravitational waves from a very different source. This is the South Pole. This is a detector that looks at radio waves, not radio waves from stars, but radio waves from the Big Bang. Microwaves, actually. It turns out that there's radiation called the cosmic microwave background radiation that is a remnant of a time when the universe was only 300,000 years old. At that time, matter and radiation the matter was so hot, it was 3,000 degrees, that matter and radiation were in equilibrium. But after that time, the matter cooled down, neutral atoms formed, and the neutral atoms were transparent to the radiation, so the radiation could move throughout the universe unimpeded. And in 1965 or so, that radiation was detected for the first time by two people who didn't know what the hell they were doing. They had a radio telescope and they looked up, and they saw noise. They didn't know what the noise was. They cleaned out, it was an outdoor telescope, they cleaned it out. It had a white dielectric material, which was pigeon droppings. They cleaned that out. The noise went down, but it was still there, and it bothered them till some physicists down the road at Princeton University told them they discovered the noise from the Big Bang. And those people who discovered it and didn't know what the hell they were doing won the Nobel Prize. Because you don't have to know what you're doing to win the Nobel Prize. You just have to do it. Okay? They discovered the afterglow of the Big Bang, the first definitive evidence that the Big Bang really happened. And the Big Bang did really happen. And if you meet anyone who doesn't think it happens, ask them if they also think the Earth is flat. Because there's as much evidence for one as the other. Okay, so we build detectors now, and this is in the South Pole. Why? Because the South Pole is dry and high, and so you can the atmosphere allows the radio waves, the microwaves, to come in a certain region of the frequency band very effectively. So this is at the South Pole. This is a detector called BICEP. And then there's another telescope called the South Pole Telescope there looking at this. It's interesting to me. This is liquid helium, which is delivered. It's cold at the South Pole, in case you wondered, but it's not cold enough. In order to make these detectors work, you have to cool them down to almost absolute zero. And so we have to ship down liquid helium to the South Pole in the summertime. This is the summer. Why? This surprised me when I first learned it. Maybe it won't surprise you, but it really surprised me when I first learned this many years ago. We don't send planes down to the South Pole in the wintertime because we're worried that if the plane lands, it won't be able to take off again. So that means if you're down in the South Pole and it starts to be winter, you're stuck there for the whole winter. That's why this is one of my favorite pictures. This is a picture from this telescope at sunset. Sunset happens once a year in the South Pole. Because in the summer, the sun is always above, and in the winter, the sun is always below. So this is the moment when it begins to be winter, which means if you take this picture, you're stuck there for 6 months, which is why it was probably taken by a graduate student, because they're the ones we send down there. But this detector, and others like it, may detect gravitational waves from the Big Bang. And I want to talk about that a little bit, and I'll even have an equation, because I felt that there are students and faculty, so I should have at least one equation in this. So here's what we think happened at the beginning of time. The universe is expanding. It's getting bigger and bigger and bigger. And if we go back to a very short time after the Big Bang, a millionth of a billionth of a billionth of a billionth of a second after the Big Bang, we think something very strange happens. For reasons I'll talk about in a moment, we think that the size of the universe increased dramatically in a millionth of a billionth of a billionth of a billionth of a second. The universe increased in size, in volume, by 10 to the 80th. It went from the size of the entire what is now the visible universe today, went from the size of being about the size of an atom to the size of a basketball. Now, if gravitational waves are produced when extreme movement of matter happens, when our whole universe goes burp, that should produce gravitational waves. But in a very particular way. And I want to show you this is the equation part, so some of you can sleep now, and then in a second you can wake up. There's a miracle. It's not really a miracle, but there's something amazing. Right now, maybe some of you who work in physics departments are working on the development of quantum materials like quantum computers, trying to use the weird properties of quantum mechanics and manifest them at human dimensions. Because we tend to think quantum mechanics only operates at small scales. In fact, you are all remnants of quantum mechanics if inflation happened. Because inflation happened because quantum fluctuations become us. We think what happened during inflation is that there was some field, like an electric field, but a different kind of field, that gets stuck in a certain place and it stores energy. And there's energy throughout space. And the field gets stuck. It's like supercooling water. On a cold day like today, you'll see, when cars go on the road, you'll see liquid water. It's because the cars are stirring it up. Even if it's below zero, it'll still be liquid. But the minute the cars stop stirring it up, suddenly it freezes, forms black ice. In that moment when it freezes, it releases energy Because the preferred state it wants to be is ice, and you've been stirring it up and giving energy, and when it freezes, it suddenly releases energy. It's called a phase transition. We think in the early history of the universe that our universe got stuck like water. It was in a phase that stored energy, and then when that energy was released, all that energy got turned into heat and particles, and the hot Big Bang happened. But during this time when that energy was stored, that's when space suddenly expanded very fast. Now, how do we know when the transition happens? If the universe is staying there, if there weren't for quantum mechanics, it could stay there forever. The phase transition might never happen. But quantum mechanics tells us that things are fluctuating all the time. And fields, quantum fields, fluctuate all the time. And I'm not going to go into this much, but they change. This field is wiggling back and forth depending upon the expansion rate of the universe, it turns out. And if it's wiggling back and forth in one place in the universe, it can wiggle so far that it falls over the edge and releases its energy. So here, inflation ends a little bit before here. But if inflation ends a little bit here before there, it turns out the density here is a little bit lower than it is here. The energy that's released is more here than there, because this happened later than that. And that means you have small fluctuations in matter and energy. But those small fluctuations in matter and energy, if you produce a little more matter here than there, it's denser here and there, that collapses to form a star and planets and people. We would not exist if it weren't for those quantum fluctuations. You are quantum fluctuations. You're remnants of quantum fluctuations if this is true. It's something we don't talk about enough, but it's an amazing, remarkable miracle, and we can calculate how much it is, it doesn't matter. But it really means that if this is true, then all of the stars and galaxies and planets and aliens and people and everything came from quantum mechanics in the earliest moments of the Big Bang. But gravity, we think, is also quantum mechanical. And if there are fluctuations in other fields, there'll be fluctuations in gravity in the early universe during inflation, and those fluctuations during inflation will get frozen in as gravitational waves after inflation ends. So the picture of the universe that we have, if this is right, and this is hard to read, but it was from a Scientific American article I wrote a long time ago, and I spent a lot of time with the artist, so you have to look at it. But we think there was the Big Bang, then inflation happened, and the universe suddenly blew up, and then it started getting bigger and bigger, and this is the time of the cosmic microwave background. And what happens? During inflation, you produce gravitational waves of all frequencies. A period of 1 second, 10 seconds, a century, 1,000 years, 1,000,000 years. What happens? Well, let's say you have a gravitational wave that has a period of 1 second. But the universe is 1/10 of a second old. Well, the gravitational wave doesn't start to vibrate yet. Space doesn't start to vibrate because there's not enough time for it to start to vibrate. But when the universe becomes 1 second old, the gravitational wave starts to vibrate, space starts to vibrate, and then that gets dissipated away. It disappears with time. Then maybe I have a gravitational wave with a period of 1 century. When the universe is 100 years old, that gravitational wave starts to vibrate, and then it dies out. And then maybe I have a gravitational wave of period 1,000 years. When the universe is 1,000 years old, it starts to vibrate. But then let's say I have a gravitational wave of a period of 300,000 years, which is the moment this microwave background forms. That will produce a remnant signal in the microwave background, and here's how. The microwave background happens because there are free electrons. The universe is hot, and electrons are free. They're not in atoms. Radiation is all around it, and the electrons scatter the radiation to us. And that's what we see as the microwave background. But if you have a gravitational wave of period 300,000 years, when the universe is 300,000 years old, that looks like the whole universe for that electron. And if the gravitational wave comes by, the universe gets a little smaller in that direction and a little bigger in that direction as far as the electron is concerned. And that means the universe looks a little bit hotter in that direction and a little bit colder in that direction. And that means the electron will scatter more radiation coming from this direction than that direction. And that means the radiation we see will be polarized. If you think about an electron and you see more radiation, intense radiation coming from this direction and that direction, you can calculate that the scattered radiation will be polarized. So if we can look for polarization in the microwave background, it'll be a signal of a gravitational waves, because the gravitational wave will have squished space in this direction and expanded it in that direction. It turns out the polarization is a little more complicated, but I'm not going to go into it here. So what we could in principle do is look at the hot spots and cold spots in the microwave background, and this we've been able to actually measure these hot spots and cold spots. We've been able to measure what we think are the fluctuations coming from the Big Bang in this microwave radiation. A Nobel Prize was given for this measurement. These hot spots are about 1/10,000th of a degree hotter than those cold spots, so it's hard to measure, but it was measured. But if we could also measure the polarization of the radiation, maybe we could see gravitational waves. So the polarization should be random if there are no gravitational waves. If there are gravitational waves, it doesn't look very different. It's really hard to see the difference. It's about 10,000 times harder to see the polarization from due to gravitational waves than it is to see the temperature difference. But experiments are being built at the South Pole now that may be able to detect that. And if they detect that, they will be seeing gravitational waves not from black holes at 1.3 billion light years away, but they'll be seeing gravitational waves produced when the universe was a millionth of a billionth of a billionth of a billionth of a second old. We'll be measuring what the universe looked like at the time of the Big Bang. And this signal can only come from inflation. And if that's the case, we'll be able to experimentally measure what happened when the universe was born. And what makes that interesting to me is not just that we're able to do that, but it turns out because inflation predicts that the universe gets much, much bigger, more quickly, our visible universe could just be a small part of what we now call a multiverse. And it could be that one region ends inflation now, creating the universe we see, but there could be other regions far away which are still inflating and haven't yet ended inflation. And there could be many, many different universes. And in each universe, the laws of physics could be different once you leave inflation. This idea called a multiverse, lots of theorists are thinking about it, but it sounds like religion or philosophy, not science. Because who could measure other universes? We'll never be able to measure them directly, but if we could measure gravitational waves from inflation, we could see if inflation happened, and we could infer indirectly that there are other universes. We could infer indirectly that maybe there are other universes, and in our universe there are galaxies, and other universes there may not be. We could turn metaphysics into physics. And any time you could turn metaphysics into physics, it's a success. Because metaphysics is just talk. Physics is real. On the scale of things, religion is down here. And metaphysics, thank you, that's true. Metaphysics is here, and physics is here. And anytime you can go in that direction, it's a good thing. So we are on the threshold in your lifetime, maybe, of being able to detect a signal from the Big Bang and maybe begin to learn about the origin of our universe. That's the astronomy and physics of the 21st and 22nd centuries, and you will be able to participate in it. And so I think when we look at this night sky, as I say, it inspires me. I hope it inspires you, but it's just the tip of a cosmic iceberg. What we can see is far from all that there really is. Earlier today I talked about dark matter, but the universe is full of things. There's far more in heaven and earth than are dreamt of in our imagination, and if we keep looking, we'll be surprised. And I hope in your lifetime you will have many, many surprises. Thank you very much. Thank you. Thank you.
Let's thank Professor Krauss for interesting lecture. And now we are continuing our program. And now we can possibility to ask Professor Krauss.
I took longer than
questions.
Yeah, I took longer than I thought, as often happens. But we'll still have time for some questions.
I think that's all right. With time, we have about aisle
well, we won't take too long. People have to go to the bathroom, but we'll take some questions. Okay, so did I see a hand? Is there a microphone, or do you want people to...
you must go to the...
You have to go to that microphone so people can hear you. And it has to be in English, or if it isn't, someone has to translate.
And now you must go into this microphone, yes.
Okay.
Microphone.
Hello? Yeah, so it's okay with English.
Okay.
So can you hear me?
I can hear you, but I'll get closer.
Okay. So if possible, I would like to ask 3 questions.
Maybe. Let's see if your first one's any good.
Yeah. Okay. The first question about the detection of the black holes collision.
Yeah.
So if this event was detected right after the turning the detector on, so that probably means that this event is quite often in our
That's a very good question. I'm going to allow you one more after that, because it was a very good, you're right. We predicted, what's amazing, and it still amazes me, is people thought that these black holes might exist, and in order to be able to get the National Science Foundation to give $1 billion to build it, they had to say, well, probably if this detector gets to the sensitivity, we might detect an event every few weeks or every month. We think they're that frequent. But it was a lie. I mean, it wasn't a lie. It was the best idea we had, but no one knew if we were right. What's amazing is, as far as we could tell, there may be 7 or 8 more events that have been seen. They probably occur on a level that is about what we thought every month or so. They were very lucky to see it within the first hour, but they've seen a few more. But the best event they've ever seen, the gold-plated event, the best one so far, has been the very first one. So it was just blind luck. It was, you know, science happens by luck as much as anything else, and they were very, very lucky. But so we think that indeed, we now know, and we didn't know before, that our galaxy and the universe is full of objects that are solar mass and bigger that are black holes. And maybe that will explain why there are large black holes in the center of galaxies. It's a whole new field of study that is just beginning. Second question.
Second question. If I understand correctly from the construction of the detector, it can only say that the gravitational wave exists, but not to direct the direction. So how can you say about the direction?
Ah, good. Well, with one, you can't. But if you have 2 on different sides of the Earth, and you measure time differences between the signal seen here and the signal seen there, so there's one in Hanford, but there's another one in Europe called Virgo. And with the neutron star, if you measure the time difference, you can sort of tell what quadrant of the sky. If you do 3, you can do better. You use triangulation. Just by measuring time differences between this signal, and that signal, you can say which direction it's coming from. And when Virgo, with the original detector, you couldn't tell really very clear. You could tell which hemisphere. But for the neutron star event, which was seen by Virgo as well as LIGO, you could actually do a region of the sky, and the more gravitational wave detectors that come online, the better we'll be able to do. But you're right, with one detector, you can do only marginally, you can sort of tell where in which hemisphere it is. Okay? But from the amplitude and the period, we can tell how far away it is. Because we solve Einstein's equations, and we know how massive the stars are, and we can see from the strength of the signal how far away the star must have been. So that's how they know it was 1.3 billion light years away. But we don't know where it was, really. But it's a very good question. I think I'm only going to give you 2, because there are 2 more people behind you. You can wait, and you can come back for the third, okay?
Okay.
Okay, thank you.
And I think it will be interesting if you say, what is your affiliation? And another.
Yeah, okay. My name is Andriy Derzhepolsky from the Institute of Physics.
Yes, National Academy of Science of Ukraine.
Yeah.
Another question.
Okay.
What is your affiliation, please?
My name is Eugene, and what did you ask me?
Where are you
What is your
from?
affiliation, organization?
Actually, no, I have already finished university 10 years ago, so
Okay.
I'm just working.
Well, welcome back.
Yeah.
Okay.
Thank you.
Your question, please.
Okay, first short, can I sign your book after the lecture?
Yeah,
It's
sure.
just short.
Okay, that was easy.
And now is the question, Mr. Krauss, what do you think about our possible encounter with extraterrestrial civilization? Is it dangerous for us? Like, for example, Stephen Hawking said about that it can be like.
Well, Stephen said lots of things.
Yeah.
Look, the likelihood of ever interacting with an extraterrestrial civilization is small, even if they exist. First of all, we don't know. We may be alone in the universe. We don't know. We don't know what the probability of life. We don't yet know how life forms here on Earth. We have ideas about what processes led to the development of life, and then we don't even know what the likelihood that intelligent life forms is. So it could be very, very rare. But even so, the universe is very large. Even our galaxy is very large. And I once worked out in one of my books the likelihood of detecting life in our galaxy, even if it exists, intelligent life, is still very remote. So I'm not worried, first of all. I think it's highly unlikely. But even if we did detect it, I think I disagree with Stephen and other people who are worried about this. Because I think the highest likelihood is detecting, if you could detect a civilization that was intelligent, it would probably have been technological much longer than us. Which means that it would not be interested in us at all. I mean, we wouldn't be a threat. Moreover, who the hell cares? Because they're not going to come visit us. We may find out about extraterrestrials, but they're not sending spacecraft to us. We just can't send spacecraft throughout the galaxy at anywhere near the speed of light. It's just impossible. Okay, and so people aren't being kidnapped with weird sexual experiments by aliens, no matter what you read in the newspaper. And so I don't think it's a worry at all. And I think Richard Feynman put it well. He said the experience of extraterrestrial sightings, UFOs, is probably much more likely due to the known irrationality of humans rather than the unknown rationality of aliens. Okay? No, don't worry. Okay, good. Okay, good. Well, there are a lot of questions.
Good afternoon, Dr. Krauss. Thank you so much for the lecture, actually. And
thank you.
Well, my name is Igor. I'm still studying at school, so
good.
Maybe my question will be a little bit stupid, but
no, there are no things.
All in all, okay. So I read that Hawking radiation is like a hypothetical process. Yeah. So how could we theoretically detect it?
Well, okay, so Hawking radiation, what Stephen Hawking did that made him famous in the scientific community was the realization that classically black holes are so dense that not even light can escape. Why? Because from Earth, in order to escape the gravitational attraction of the Earth, you have to send something up at a speed of 11 kilometers per second. Any of the introductory physics students here could calculate that, I hope, because this isn't the United States. And so, but if I added a little bit more mass to the Earth, then the escape velocity would increase. And if it gets more massive still, the escape velocity increase. And if I get enough mass in a small enough region, the escape velocity is faster than the speed of light. But nothing can travel faster than the speed of light, so not even light can escape. Light comes back on itself. So nothing can escape a black hole. But what Hawking discovered is due to quantum mechanical processes near something called the event horizon of a black hole, particles can actually escape. And the black hole will evaporate. For a solar mass black hole, the time it takes it to evaporate will be far longer than the age of the universe. But for a small black hole, it can evaporate in an instant. But the problem is, The only black holes that evaporate quickly are the small black holes. But you can't see small black holes unless they happen to be in the room, and there aren't any. So the likelihood of ever directly detecting Hawking radiation is almost zero. It remains a theoretical prediction. But it's a very important theoretical prediction, and I've worked on it, because if black holes do radiate, then there are various paradoxes that happen, because you can have material fall into a black hole and then you don't know what's in there. And then the black hole disappears, and where did all the information go? In quantum mechanics, the information can't disappear. But if the black hole disappears, the information has disappeared, so it appears to violate the laws of quantum mechanics. And that's why many of my colleagues are fascinated by the idea of black hole evaporation, because it appears to violate the tenets of quantum mechanics. And maybe we'll learn something about quantum gravity, but unfortunately, it's likely to remain pure theory. And that's why right now there's much more heat than light, if you are being talked about. And most of it is just talk. Okay. Yeah, thank you.
Thank you very much.
Thank you, it's a good question. Okay.
Good evening, my name is Mikhail. I'm from Institute of Physics and Technology from KPI. I want to ask you a question about the warp engines and Alcubierre engines. In previous 30 years there was a bunch of theories about this kind of stuff, and I want to ask you a question. How do you think can we achieve some results in this in following years, or maybe in this century?
Sure, I wrote about that many years ago in the Physics of Star Trek book that I wrote. The idea is, you know, you've heard of Star Trek, right? Okay. So the problem with science fiction, well, it's not the problem. The problem with real life is that we can't travel faster than the speed of light, and the galaxy's big. So we're 30,000 light years from the center of the galaxy, and therefore if we want to explore the galaxy, take 30,000 years to get there. That does not make for exciting television. 30,000 years is a long time. So they had to come up with something that allow you to go through the galaxy faster than the speed of light. They called it warp drive. And it was easy for the writers, but it's not so easy in the real world. But it turns out, when we say that you cannot travel faster than the speed of light, we're lying. We have to be a little more careful. You cannot travel through space faster than the speed of light. But space can do whatever the hell it wants. And space can expand at far distances faster than the speed of light. So if you could manipulate space, with general relativity, you could be standing still and still moving at the same time. We're doing that right now. We're standing still relative to each other. But relative to an audience in a university on a planet around a star at the other end of the visible universe, we're moving away at the speed of light. And that audience in that theater, in that planet around that galaxy, they're also at rest. So they're at rest and we're at rest, but we're moving away at the speed of light. Why? Because the space between us is expanding so fast. So if you can manipulate space, in principle, you could imagine traveling faster than light. And this is the idea, it's quite simple. So you want to get from here to the nearest star. It takes 100,000 years for a rocket to do it, let's say, with conventional rocket. Voyager will take that long to get to the nearest star. But all you have to do, if you can manipulate space, is to arrange for the space between you and the star to collapse in a fraction of a second, and the space between you and the Earth to expand in a fraction of a second. And then you're there you didn't move, but the space did all the work. And now you're near the star and you're 4 light years away from the Earth. It sounds easy. Not so easy. In principle, the equations of general relativity allow that to happen. The question is it possible in practice? And the answer is probably not. If you could do it, the amount of energy that would be required is large. It's changed. We used to think it'd be greater than the mass of the visible universe. Then it was just the mass of the galaxy. Now maybe it's just the mass of the Earth. But it's not practical. Even if we could do it, we don't know how to do it. We don't know how to create the type of energy in the laboratory that would make space expand. We can create the type of energy that makes space collapse, that's us. But the type that makes it expand, we don't know if in principle that can be created in the laboratory. But even if that were the case, by the way, just to take away all your hope, you still can't travel faster than light. Namely, let's say I want to go from here to the nearest star. Well, to make space collapse between me and the nearest star, I'd have to populate it with the right amount of energy. But the only way I could do that would be to have with rocket ships dumping the energy there, and those would happen at lower, they can only travel slower than the speed of light. So to set up the experiment would take 100,000 years. Then poof, it would happen like that. But from the time you started the experiment till the time you made it happen, you don't win anyway. So it's wonderful for science fiction, but I wouldn't go into business trying to make one. Okay? Okay, good.
Thanks a lot.
Sure, thank you.
I'm sorry, just a moment. Professor Krauss, we have a limited time before ending of its lecture, and maybe we can give a more smaller answer.
Okay, a much smaller answer. I talk too much, is what he's saying. Okay, I'll be quicker. Yeah?
Okay. Hello, my name is Yuri. I hope you enjoy being here in Kyiv.
I'm enjoying talking to you immensely.
I'm not... Oh, thank you. I'm not a physicist, I'm an engineer.
That's okay.
So my, so my question would be more practical. When we have some waves in air, for example, it changes the density of
that's because normal
air, yes.
Okay, go on.
So when we have those gravity waves, it should have changing the density of the matter of the space.
It does. That's why space gets hotter in one direction than another in the cosmological background.
It should affect the optical properties of the light, and probably this sensor would not work.
Well, it wouldn't work. Your point is well taken. And every time I've thought about gravitational waves, I got confused for the same reason. You'd think that the light would change in such a way that you wouldn't see the effect, but because the two beams are going through two different gravitational fields, they change it. If one beam could never do it, but because the two are experiencing different gravitational stresses, they will interfere differently. And that's the reason you get interference. Because for a long time, people, even Ray Weiss, had convinced himself that maybe the effect wasn't real, that the effects would cancel out. But because the two beams are going through two different gravitational trajectories, they do interfere. But it's a very good question. You should become a physicist.
Okay, thank you. I'll try.
Thank you. Thank you. Yes? You can put it down. There we go. Okay.
Hello, my name is Angelica. I'm studying applied physics in this university. And wow, enormous numbers. But don't you think that your researchers are take place in mostly in philosophy, not in physics?
Don't I think it's more philosophical than physics?
Yes.
I hope not. No, because the difference between philosophy and physics is, again, if you can measure it, it's physics. And if you can make predictions. Philosophy, look, many people know I've made fun of philosophy often, and I like to because it's easy. But the point is, philosophy is useful for reflection about trying to think critically about what we understand. But making predictions, physics is a very mature field. And we can make very mature predictions that can be tested at the level of 10 decimal places. And so that's not philosophy. And so we can make, the fact that we can predict the fluctuations in the microwave background to 1 part in 100,000.
Just because we can calculate it.
What was that? But it becomes philosophical if we begin to make predictions about the origin of the universe. Right now, that leads to a whole bunch of philosophical questions. And those are interesting to ask. But what interests me far more than those philosophical questions is the physics answers. I mean, we can philosophize about what happened before the Big Bang or whether there are many Big Bangs. It's wonderful to talk about, but who the hell cares? What I'd like to know is, can we measure what happened at the Big Bang? That's what interests me. And I don't know if we'll know the answer, and I don't know if we'll ever know what happened before the Big Bang, but we'll never know unless we try. And so we just keep trying. That's all.
Thank you. And my second question.
Okay, you get two.
Only please, short question.
No, give her
yes?
two. Yeah, okay.
Okay, we have a Big Bang, and then a star dust.
Yes.
I think that it's a little bit stupid to search gold just on Earth. Don't you think so?
It's stupid to have gold just on Earth?
Search gold just on Earth.
I don't understand what you said.
If we have gold from the Big Bang.
We don't have any gold from the Big Bang. We have the gold. The only place gold is created, and the heavy elements we think are the collision of neutron stars.
Yes.
And that was a prediction. And what's amazing to me is that prediction was verified explicitly when we observed the collision of those neutron stars. Exactly the radiation that came from the decay of radioactive nuclei that was predicted was seen. So it's amazing that our theoretical ideas about where gold and the other elements heavier than iron were created was exactly validated by observation. That turned philosophy into physics. Okay?
Angelica, I give answer on the question at last week in our lecture, okay?
We probably won't. Okay. Yeah. Okay. We've got to. Well, maybe we should end at 3:30. Is that okay if we end at 3:30? Just so people know they're getting restless. Can we end? We'll end in 10 minutes. Okay. So, and then I'll answer questions in private. But you're not stuck here. Yes.
Good day, Professor Krauss.
Hi.
It's a great pleasure to have you here today.
It's a great pleasure to be here.
My name is Alexander, and I'm not a student. I just came here from work.
Good.
Left my workplace.
Good.
The distortions of the space-time that we measure are...
Get your face closer to the microphone.
Yeah, sorry.
No, it's okay.
The distortions of the space-time that we measure are extremely tiny.
Tiny, yes.
And also we should hear a lot of noises produced by driving cars around the detector, maybe.
Oh, I mean, there's an incredible, I mean, it's amazing that you can, in the midst of all that noise, you can see the signal. Again, if you'd asked me if I ever thought they could do it, I was sure they couldn't.
No, I just, as I know, scientists look for patterns modeled before of the known types of collisions. Is it possible to find a signal, to detect a signal from a known type of collisions? For example, aliens may be making fun with stars.
No, it's a very good question. The answer is there's an old story that I like to tell. Well, it's a famous story. None of you have ever experienced this, but let's say you get drunk and you're in a bar and you walk out of the bar and you're hobbling around and you've lost your keys. Where do you look? You look under the light post. Why? Not because the keys are going to be there, but it's the only place you'll be able to see them.
Yeah.
So if we're physicists, what we do is we always look under the lamppost. The first thing we do is we look for what we expect. Okay, because that's easy. The second thing, once you know your system is working and you know what to expect, then you can begin to look for the surprises. So the answer is yes, maybe we'll see something we didn't expect. In fact, everyone hopes that. But we don't know what we don't expect. And so we just look. But the answer is, in order to be separated from known sources of noise on Earth, you'd have to see the same signal in many detectors at the same time. And if you saw something that was, very, very different than a colliding star, then maybe it would be a signal from an alien civilization. But you know what? There's a lot easier ways of signaling. I would do this with my laser beam, okay? It's a lot easier to do that than make a gravitational wave. But maybe sufficiently advanced civilizations can manipulate space enough to do that. Who knows? You never know till you look. So it's a good question.
Okay, thank you so much.
Yeah, sure.
Hello, my name is Vlad. I'm not a student anymore. I have a question regarding Doom's clock.
From which university, please?
Sorry?
Which university?
National Aviation University. I left 10 years ago.
Doesn't matter.
Maybe.
Okay.
Okay, doesn't matter.
It matters to him. Doesn't matter to me. Okay.
Doom's clock. How much time it shows right now?
How much time what?
It shows right now.
How much time? I didn't understand. How much time what show?
Doom's clock.
Oh, doomsday clock. Oh, yeah. Okay. Right. Okay. Well, I've been involved in something called the doomsday clock. I headed the Bulletin of the Atomic Scientists for many years, or at least the committee, this group of sponsors. And it's now 2 minutes to midnight, which is as close as it's been any time since 1953. So what we said is that the threat of nuclear war and climate and the effects of climate change and maybe other kinds of terrorism is very great right now. And we think it's a very dangerous time in the world. Now, what do we mean? Why do we do that? Not to scare people, but to tell people the only way we're going to change things, the only way we're going to change things is if you get interested and you get worried and you make your governments change. The only way they'll deal with climate change is if the public starts to complain. The only way they'll do nuclear weapons agreements, as you may know, my idiot president has just abrogated an arms control agreement with Russia. The only way that's going to change is if the public gets involved, and the only way the public's going to get involved is if they begin to worry about it. So one of the reasons we produced the Doomsday Clock since 1947 is that. The first people who set the Doomsday Clock were Albert Einstein and Robert Oppenheimer, and I was honored for a decade to head that group. I no longer, as of about 5 months ago, I no longer head that group. So I don't know what the Doomsday Clock will be set at next year. But I was very honored to be involved, but the point wasn't to scare people. It was to just get people to act. Because it's only, the governments don't lead, they follow. Even dictatorships follow. And the only way to make change is have the public make the change. And so that's why we did what we did. Okay.
Hello.
Hi.
I'm on the second year studying here in Kyiv University.
Okay.
My name is Melnik Kola. And I would like to ask you a question about string theory. Can we prove the string theory using gravity waves?
Well, look, the point is, in order to prove, well, in physics we don't prove things, by the way, we disprove things. No, I can never prove an idea is right, I can only prove it's wrong. What's left over may be right, but it can always change. But the only way to disprove string theory would be if it made a prediction. But since it hasn't made any predictions, then it's hard to disprove it. And it's not a fault of string theory, it's a very complicated idea that may or may not have anything to do with reality. But because it deals with phenomena that are so esoteric that even if we understood the math, and we don't yet, then it's not clear we'd be able to make predictions that could be detectable. Maybe if we could probe the very beginning of the Big Bang at the level I talked about, maybe we'd begin to test physics that might be relevant to string theory, but I wouldn't hold my breath. Right now, calling string theory a theory is really an insult to the word theory. That's nothing against string theory, but theory in science is something that's been tested, like the quantum theory, theory of gravity. I mean, these are ideas that have been tested over and over again. String theory is really a hypothesis. It's a very fascinating mathematical hypothesis that maybe relates to the universe in which we live and has good and is well motivated on certain grounds. But it's far from, unfortunately, it's not even yet well enough defined to be able to provide tests that we can do to know if it's false. So it's not yet even a theory.
Thank you for the answer, and thank you for your speech. It was really interesting.
Thank you, and thank you for the questions.
Please, just a moment. I want to say that we have a limit of time, maximum before 4 o'clock, and I hope that your questions will be more shortly. And
I'm going to go in public for another 3 or 4 minutes until I get to that young lady, and then who's standing there. Unfortunately, you guys, I don't have time. But I'll answer your questions in private. Sorry, so after the young woman in the heart sweater, that's where we'll end. So let's go. You're the last question.
Last question, please.
Okay. Okay, next question.
Hi, my name is Tem. I'm from this planet.
Okay.
Yes, but I'm from the KPI. Physics chemical students.
Okay,
but
sure.
I have long time interested astronomy, amateur astronomy. I have one question. Probably theoretical physics.
Yeah.
Yes. theoretical physics already believe in the existence of graviton, but
how could we prove the existence of gravitons? Is that your question?
Yes.
Actually, that's it. Okay, I'm going to be faster now. I'm going to anticipate your question. In quantum mechanics, every wave is associated with a particle. If gravitational waves exist, then the quanta of gravitational wave called graviton should exist. Now, what's really interesting is there's no experiment you can do on Earth to measure gravitons, we think. But the universe may allow us to measure gravitons. And in fact, if you could measure gravitational waves from inflation, I and a colleague of mine, Frank Wilczek, who won the Nobel Prize, have shown that you could prove gravitons exist, in principle. If you could measure gravitational waves from inflation, we think you can show that gravitons exist. So that may be the only way to show experimentally that gravitons exist. That's why I'm so interested in that. That's the quick answer. I'll answer more after that, but I want to get through, okay?
Yes.
Okay, thank you.
One more question. One more question.
Well, I can't let you ask another question now because I want to get to, you can, hey, don't get mad because I'll be here. You can ask me the question in private afterwards, okay? Okay.
Hi, I'm a student of KPI, and my question is about the false vacuum.
False vacuum.
Yes. Actually, when you were talking about that, where did the universe get the energy to actually push the state of conservation of energy?
Well, the neat thing, okay, look, when he mentioned the word false vacuum, when I showed you inflation, I showed you that we were stuck in a state and then it released the energy. That's what we call a false vacuum in physics, okay? So the universe gets stuck in some state that isn't the true ground state of the universe. Where did the energy come from? Turns out it's great. It's the ultimate free lunch. Because it turns out that while empty space has energy, in that case, that gravity has negative energy. And the two balance and you can have zero total energy. So the total energy of the universe can be zero. And that's why I wrote a book called The Universe from Nothing, because it turns out the total energy of our universe may be zero. The positive energy, due to galaxies and everything else, or in early times due to the energy of empty space, can be countered by the negative energy of gravitational attraction. The two can add up to zero. And if you look at our universe, it looks like the total energy is probably zero. So it's the ultimate free lunch. You can get a universe full of 100 billion galaxies from nothing without violating any laws of physics and without any supernatural shenanigans. Okay? Okay. That's the quick answer. Yeah?
Hello, my name is Dima, and I want to ask you about sounds of Big Bang, which some mechanics hear, but didn't get that was a Big Bang. Like, how does it relate it to radio waves, and how can they even hear it?
Well, I'm not sure 100%, should you 100%, but the point is that when the Big Bang happened, after the Big Bang, the universe was very hot. And then over time, it cooled down. And matter and radiation were in equilibrium because you couldn't have atoms. Because every time a proton captured an electron, it would get kicked out again by the radiation. So you had ionized matter. And when matter is ionized, it's always in equilibrium with radiation. But when the universe cooled to a temperature of 3,000 degrees, protons, the nuclei of hydrogen, could capture electrons to make neutral hydrogen. Neutral hydrogen is now transparent to that radiation. So the radiation that existed at that instant has now been able to move through the universe unimpeded. So that radiation, which was 3,000 degrees, has cooled now to a temperature of 3 degrees. And if you asked what frequency would the radiation having a temperature of 3 degrees be, it would be in the microwave band. So we look at microwave radiation and we see it in all directions, and that's the remnant of the radiation, the hot Big Bang radiation that got decoupled from matter when the universe was 3,000 degrees in temperature, which happened at a time when the universe was 300,000 years old. And that's why that picture of that microwave background radiation gives us a picture of what the universe looked like when it was 300,000 years old. That's the quick answer. Okay?
Thank you.
Sure.
Oh,
2 more questions. Okay.
I am a physics student, and my question is regarding the polarization.
The microphone, please.
Sorry, what?
No, it's okay. It's okay.
Okay, sure. How many polarizations are in the gravitational waves?
Well, gravitational waves have two polarization states.
Okay, then I have another question. We all do know...
I knew that was a trick
We all do know
question,
that
so it's okay.
graviton is a tensor-like particle and has spin 2.
Yeah, I know.
And
But it turns out gauge invariance reduces all the extra degrees of freedom. Just like the photon... I know you have a smart question, so I'm going to give you a smart answer. The photon should have 3 degrees of freedom, because after all, it's a vector field. Vectors have 3 degrees of freedom. But it turns out the symmetries of nature, something called gauge invariance, reduce one of those degrees of freedom. So photons have only 2 polarizations. It turns out there's a much bigger set of gauge invariance for gravitational waves that takes something that should have 8 or 9 degrees of freedom, and because it's a tensor, and reduce it to just 2 polarizations, and that thing is called gauge invariance. Okay, that's the mathematical answer to your question.
Okay, so what is the group of symmetry?
What?
What is the group of symmetry? We know that photon has U1.
It's conformal. It's the general coordinate invariance of general relativity, which turns out to be a gauge symmetry.
I know. What is the gauge group of symmetry?
Oh, well, it'll be SL3C, I guess.
Which theory?
Anyway, we can talk about that. Okay, it doesn't mean anything to anyone here, so we'll have that conversation.
Now we say about only classical Faraday gravitation. Please, just theory, not about quantum generalization.
Okay, last question.
Okay.
It better be a good one.
You said that multiverse may exist if there are any other universe. May modern science predict what may they look like, what may they be like?
What be like? I'm sorry, I didn't hear. What? Oh, what may the other universes be like? Who the hell knows? No, seriously, because this is all speculation right now, and it could be that there's only one set of laws of physics and they're the same. After inflation, there's only one possible state that the universe can come into, and every universe it forms has the same laws of physics. Or it could be that they're all different. It could be that every possible kind of laws of physics exist anywhere. We don't know. Once again, the only way to know is to try and do the experiments to try and understand the nature of inflation. And the only place to find and understand the nature of inflation may be to look for gravitational waves from the Big Bang, or to look for new exotic physics in particle accelerators. So the answer is, it's anybody's guess. And it's your job in the next generation to find out. Thank you very much.
Thank you so much.
Thank you. Thank you.